Hi, I'd like to talk about white dwarfs. And the beginning of the story of white dwarfs comes from first the observation of Sirius A in 1844 that there was a very slight wobble in its motion due to an unseen companion. In 1866, the very fine telescope maker Alvin Clark built a telescope and was able to observe this very faint star, Sirius B, and also it was found that these are indeed a binary. So these stars orbit their common center of mass, which means they are the same distance from us. These two stars are roughly the same distance. They're orbiting each other. They're the same distance from us. So why is one terribly bright and one very, very faint? Well, we know this one is bright, or suspect that it's bright because it's a close by star. But this one would have to be close by and very, very faint. And so these were called white dwarfs because the spectrum showed that they looked white or bluish white, and they were very faint. And the reason why they're faint is that they are very small. White dwarfs are about the size of the Earth. And if we look on the HR diagram, this is where, after a number of these were discovered, they all lie somewhere over here in the HR diagram. And the star Sirius A is an A0 star, so it's very, very bright up here on the HR diagram and much, much brighter than its companion Sirius B. So those are the white dwarfs, and we now know that they are the end stage of a star like the Sun. And here is a diagram, just not an actual photograph at all, just an illustration of the size of the Sun and the size of Sirius B here and Sirius A. So Sirius A is a little larger, but not much larger than the Sun, respectively, compared to Sirius B, which is much smaller. But we know now that stars like Sirius B, white dwarfs, are the end stage of a star like the Sun, a low mass star. So the Sun will end up becoming a white dwarf after it releases a planetary nebula. So white dwarfs have a very interesting property in that high mass white dwarfs are smaller than low mass white dwarfs. And white dwarfs are so-called degenerate objects, which means that it's a Fermi gas, and the equation of the Fermi gas gives a very specific relationship between the radius and the mass here. And so, first of all, we want to think about the units here are in solar masses. So Sirius B is almost the same as the mass of the Sun. But the radius is here about the same as the radius of the Earth. And one of the things that this plot tells us that Chandrasekhar found was that this meant that the white dwarfs have a maximum possible mass of just a little more than 1.4. It's about 1.4 solar masses. So if a mass gets added to a white dwarf, it gets smaller and moves down this diagram. So these are larger and less massive, and these are more massive and smaller white dwarfs. So if you think about adding mass or sand to a sand pile, adding more sand makes it bigger. Well, this doesn't happen with white dwarfs. Adding more material makes it smaller, and So this is a very unusual property and a very important property for white dwarfs. Now, if a white dwarf is formed at the end of the life of a low mass star and it is very close by another star in a binary, and such that that normal star is so close that the gravity of the white dwarf, which the white dwarf in this case has more mass than the normal star here, but it's very concentrated, again about the mass of the sun in the size of the Earth. And the sun is 109 times larger than the Earth, so we can consider that this is very dense material. The normal star will lose material and it will swirl around, forming an accretion disk. Here's the hot spot where the material, the stream will crashes into the accretion disk. And so this is a normal star and a white dwarf, so we could imagine that before these were two normal stars, and maybe in the future this normal star will also become a white dwarf or, as well. So this is one way we can see that things are happening with white dwarfs. If white dwarfs are isolated by themselves, then they don't do too much. They just fade away gradually, following on the HR diagram. So eventually though, if you have a binary system and material will flow onto the surface layer builds up a layer of hydrogen on the surface, and the atmosphere of a white dwarf is very thin because the gravity is about 1 million times stronger than the gravity here on Earth. And so the atmosphere is very thin and it's building up hydrogen, and the pressure and temperature of that hydrogen can get to a point where it is similar to that of the center of the sun, and therefore it will have a nova explosion on the surface. And so the surface is a thermonuclear fusion of hydrogen into helium on the surface of the white dwarf, and this causes the entire surface and the atmosphere to get extraordinarily bright and expand very rapidly. And so in just a couple of days it can go from being like this to like this, and after about a month the nova fades away. And this was called a new star. Nova meant new star in Latin, because this was a star that would suddenly appear in the sky and you wouldn't see it before. But then we saw that once it faded away, it was not a new star, just a star that had this event. And after about a month or two, at least, the nova will appear, the star will appear more or less back to its original brightness. And so the nova then is occurring because mass is transferring, and it doesn't cause the destruction of the star. A nova can repeat. It can happen again and again as more and more material flows onto the companion star, from the companion star onto the white dwarf. So the white dwarf can collect more material over time and then have the nova explosion happen again. And the nova explosion also doesn't disrupt the other star in any way. So if we think about the extreme case of adding more and more mass to a white dwarf and it getting smaller and smaller, we can think of it, I kind of think of it as a point of breakage, because how can the white dwarf sustain this process of getting smaller and smaller and smaller as more and more mass is being added to it? Eventually it breaks, and it does. The entire star explodes if you add enough mass to go beyond this limit. And this limit is called the Chandrasekhar limit. It is 1.4 solar masses. So 1.4 times the mass of the sun, and the star will just completely explode, leaving nothing behind. So this is what's called a type 1a supernova, when a star explodes and leaves nothing behind. And here's one way that can happen. You have two normal stars are in a binary system orbiting around. The more massive star becomes a giant, because the more massive star lives a shorter life, it becomes a giant. And then the lower mass star is still there, unaffected, orbiting around, going through its life cycle. Now, then, because it's grown and gotten large, the outer edges feel the gravity of the other star, and then the normal the companion here then starts receiving material from the other star. And this red giant then becomes a white dwarf, and both of these stars spiral in towards each other because there's a lot of gas and material around, because they're really inside the core of the giant supergiant star. And so there's a lot of details here. We just are kind of looking to the general perspective on this, and that we have this common envelope is ejected, then all of this gas then flows away, and that afterwards the two stars are very close together. The remaining cores of the giant collapses and becomes a white dwarf, which means now we have two white dwarfs here. And as these two white dwarfs then begin to move even closer together, this is on a much smaller scale. This isn't a giant star, and it starts losing its material to the other white dwarf, and the white dwarf then passes the limit, the 1.4 solar mass critical mass limit, the Chandrasekhar limit. That star explodes. It leaves nothing left behind. This star then would just go flying out into space. And so this is a supernova, type 1a supernova, and it represents not really the end of the life of a typical star, but the end of the life of a star making the white dwarf, but having the white dwarf also gain enough mass to pass this limit and explode. A white dwarf that doesn't have this happen will just simply gradually fade away. Sometimes that's called a black dwarf, eventually fading away, because a white dwarf is a dead star, remnant of a low mass star that doesn't have any more nuclear fusion taking place. But a nova event and a type 1a supernova event are things that can happen to a white dwarf, and after it is in a binary system, for instance. Both of those require a binary system, like a cataclysmic variable binary system. So that is a summary of the end state of the low mass star, the white dwarf.